this video we're going to have a look at what we understand by the term standard enthalpy changes. So these are ones that are in data books that we can rely on, and the word standard is referring to the fact that they were measured under standard conditions. Now the standard conditions refer to a temperature and a pressure that is used when the experiment is carried out, and the standard temperature is equivalent to 25 degrees C, but we need to give it in the SI unit of temperature, which is Kelvin. So that's 298 Kelvin, and the pressure is 100 kilopascals. That's roughly room pressure. When you're not up a hill or under the sea, it's roughly sea level pressure. So when we talk about standard conditions, we might talk about the standard state, the physical state that something is in when it's at room temperature and pressure. And we need to know that for quite a few substances at A-level chemistry. We need to know it for all the elements in the periodic table, and we talked about this in the Introduction to Chemistry unit. And we need to know it for a few compounds, common things. So do you know what state carbon is in at room temperature? See if you can put as many state symbols across here that you think these things are in at room temperature. So the one that you might have not been sure about might have been the heptane, C7H16. When we've gone through alkanes, we know that the first four alkanes are gases and then they turn liquid until you get to around about C20, which is when they turn solid. There would be no aqueous here because that's not a standard state, because you have to dissolve in water to be aqueous. So the sodium chloride would be solid at room temperature. Right. What is our first standard enthalpy change that we're going to look at then? Well, the first one we're going to look at is something called the standard enthalpy of formation, of making things. And you can see we've got a little f for formation in between our delta for change, h for enthalpy, and the little round symbol with a line through, a bit like the underground sign, refers to the standard part. So let's put that here. When we see standard conditions, we'll see this kind of underground symbol to tell us that it's being measured under the standard conditions. So the standard enthalpy of formation. Well, what's important to know is what is it talking about? It's when 1 mole of a compound is formed. From what? From elements. The elements that make it up. You wouldn't expect to form ethane, and that's C2H6, and not use carbon and hydrogen, but that's stated there, constituent. And everybody's in their standard state, so we're going to make 1 mole of the compound. What that means is you can't put a number here, because I'm making 1 mole. So it must be 1 mole. That might mean we have to have some fractions on the left to make it work, because we're forming 1 mole of the compound. So what elements is ethanol made from? Well, ethanol seems to have C's in it, H's in it, and O's in it. But is that how those elements exist at room temperature and pressure? So are these elements ones that are diatomic? Well, carbon no, but hydrogen and oxygen are. And then we can balance it. So there's 2 C's, so we put 2 C's. There's 6 H's, so we put 3 H2s. And there's only 1 oxygen, so we have to have a fraction, a half an O2. And then because the definition refers to state symbols, we're going to have to put some in. So at room temperature, carbon is a solid, hydrogen is a gas, and oxygen is a gas. Pause the video and see if you can answer the remaining 2. So our second one looks like that. Now if you've gone for S8 and put 1/8 of S8, you would get that marked right in the exam. They will accept just an S for sulphur though. And remember that only mercury and bromine are liquids, so most things are solids except for the gases that we know we've covered, which are gases. And then we've got our final one there, 6 carbon solids, 6 hydrogen gases and 3 oxygen gases to make glucose. By definition, if we were, so we can measure these and we get a value in a table. Yeah? So we might get this, and these will all be negative numbers, and the more negative it is, the more stable that compound is. But if I said to you, measure the enthalpy change of formation of oxygen gas, you would say, well, I make it from O2 gas, and you haven't done anything. So by definition, that one has a value of 0. Now that is going to be important later on in a calculation section. So by definition, the enthalpy change of an element in its standard state is 0, and the more negative a value is for this, the more stable the compound is. What you have to think about is if I had to go backwards, I'd have to put that same amount of energy in but positive, so the more energy I'd need to put in to break it up, the harder it must be to break up, the more stable it is. So there's a couple for you to have a go at there. See if you can do question 1. The first thing to realise is that formula of methane is CH4 gas. We have to make 1 mole from its elements. So you should have got that. On the next one, you have to remember the formula of sodium carbonate. At room temperature is a solid. So make that from its element. So there you go. You might have written 1.5 O2s. That is absolutely fine. And then we've got a slightly harder question here. Here we've got a question that shows us a reaction, and it's not a standard enthalpy of formation because it doesn't form 1 mole. And question number 1 is, what would the enthalpy change for formation of ammonia be? So if we write the equation for formation of ammonia, we'd make 1 ammonia from a half a nitrogen molecule, mole of nitrogen, and 3/2 H2 gas. So how does that equation relate to the one we've been given? Well, we can see it's half of everything. So the enthalpy change would be half the value. So if we halve minus 93, we get minus 46.5. Now the question says, what's the value for decomposition of 10 moles of ammonia? Now decomposition is breaking it back down to its elements. So if this breaks down, we get nitrogen and hydrogen. How much nitrogen would we get? Well, from 10 we would get 5 N2s, and we would get from 30 hydrogens 15 H2s. So how does that relate to the question we had the number for? So remember that this number was making 2. So at the very top, this number was about making 2. We're now breaking 10. So this is 10 as opposed to 2. So how do you get from 2 to 10? This is 5 times the reverse equation. It's not the same way around even, it's the reverse. So we want to do our delta H is 5 times, and instead of minus 93, because we're going backwards, it's plus 93. So that would be 465, a positive 465 kilojoules per mole. So that's just some problem solving alongside the definition. Do you really understand the definition enough to problem solve it?